All right, guys, we're going to wrap up Chapter 10 with Section 10.8 on what we call the Fundamental Counting Principle, or the FCP. Section 10.8 really talks about how many different ways you can do something through permutations, through combinations, and this method here called the Fundamental Counting Principle. So to start off, the Fundamental Counting Principle simply says, in other words, if you have a certain amount of ways to do something and another amount of ways to do something, to find the total amount of ways, all you need to do is multiply m times n. So let's take a look at an example here. In number 1, it says, how many ways can you make a high school schedule? Well, we have 3 math classes to choose from, 3 science classes, 4 language arts classes, and 2 social studies classes. So, according to the fundamental counting principle, all you are going to do is 3 times 3 times 4 times 2. That gives me 9 times 4 is 36 times 2. That gives me 72 possible ways to schedule my classes. Now, if you don't believe me that the fundamental counting principle works, what you could set up is an example of a tree diagram. So let's say that the 3 math courses were algebra, honors geometry, and academic geometry. So A, H, and G to represent those 3 classes. Each one of those, let's just say for the sake of argument, we could take biology, conceptual biology, and maybe honors biology, whatever it might be. We would have for each of those then branches B, C, H for those choices. Then we would continue on with 4 language arts courses. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and so on. By the end of this, after we did the 2 social studies classes, we would have 72 branches on the bottom here. So as you can see, it's getting a little clustered already. I'm not recommending you do a tree diagram, but just to let you know, that is exactly why the fundamental counting principle works. Whenever you multiply those numbers together, you would get that many different ways. And we're going to use that method for a few of the examples here. So let's take a look at number 2. How many different license plates can be made having 3 numbers and 3 letters? So I use pink here, and I set up 3 different slots. And for the green, I set up 3 different slots. So let's take a look at the 3 numbers. So numbers, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 numbers to choose from here, 10 here, 10 here. When I think about the letters, if you think about what your language arts teacher teaches you, you have 26 different letters to choose from. So when I go ahead and multiply those together, when I take 26 cubed times 26 times 26, we get 17,576 times 1,000 leaves us with 17,576,000 different ways or different plates that we could have in that given state. So remember, the key thing about this problem is the numbers 10, 10, 10 stayed the same. So you're going to see an example in a second here about problems where the 10 might change to something else based on the fact that you cannot repeat. But as you know, with license plates, you can't repeat. Your license plate at home might have the letters AAF and then 994 in it, whatever it might be. A lot of states have different regulations, but this is just an example of one that would work. So lots of different combinations of plates that we could come up with. Let's take a look at another one. A code consists of 3 letters, and none of the letters can be repeated. So that's now huge because we only have 26 letters to choose from to start. But say my first letter, and this is just an example, say my first letter is an A. I now no longer have the A to choose from. So I would now have 25, and then say the next letter is B. I would then have 24 to choose from, and my next letter would be C, whatever it might be. Then I need to multiply 26 by 25 times 24, and it would come out to 15,600 different codes that I could choose from to set up that password or whatever it might be. So that's another example of the fundamental counting principle, how we now cannot repeat something 26 times 25 times 24. Let's take a look at number 4. An online bank account password must consist of 5 letters followed by 3 numbers, and none of the letters or numbers can be repeated. how many different passwords can be made. So go ahead right now, fill in these 8 slots that I have here with your 5 letters, 3 numbers, and then go ahead and multiply and see what you get. Good, I'm going to pause this. Go ahead and try it on. All right, now that you're back, you should have written in your blanks 26, 25, 24, 23, 22, because none of the letters can be repeated, and then 10 times 9 times 8 because none of the numbers could be repeated, giving you a total of 5,683,392,000 different passwords to choose from. So you notice once you start adding, even adding one number on the end here is going to make this number significantly larger. Adding one letter to this password makes it significantly larger. You think about some passwords, how they say you must choose an uppercase letter, a number, as well as a symbol. So adding that symbol at the end there, once again, greatly increases your total number of passwords that a hacker could choose from, as well as increases your chance of identity theft by getting access to those passwords. So it becomes less and less likely as you make your passwords stronger and stronger. All right, let's take a look at the next slide here. We have something called permutations and combinations. Plain and simple, a permutation is something where the order does in fact matter. A combination is an example of where the order does not matter. So you think about some permutations. Order does matter. A horse race, any kind of race. The ways that I can assign kids into a row. Those are examples of order mattering. Combinations, order does not matter. Now maybe I just want to form a committee. Maybe I want to have a group of 5 people chosen from a group of 100. How many different ways could I do that? Nobody has a special rank to them. There's no president, there's no vice president. That would be an example of a permutation because now that is relevant. But in this case, we think about what is in school that does not make sense. Well, you think about your locker. Why is that called a locker combination? Should be called a locker permutation. I've been pushing that with Mr. Demar for years now. He won't seem to budge on it, but we still continue to call them locker combinations, when in fact the order definitely does matter how we enter those into our locks. Let's take a look at an example of a permutation. And also, I want to bring something up. There is an example, there's a formula in the book called the permutation formula. I am not going to teach that because you can simply use what we call a factorial to solve that. A factorial is something that counts down the numbers. So for example, if I had 7 factorial, we would be left with 7 times 6 times 5 times 4 times 3 times 2 times 1, and then multiply those across, and that gives me my total number of ways to do something. There are factorial buttons in your calculator if you want to take a look at where to find them. All calculators are different, so I'm not going to go over that right now. But here we have 6 horses in a race. So once again, let's set up my 6 slots. 1, 2, 3, 4, 5, 6. And how many different ways can those horses win? Well, they can win 6 different ways. Once Prickly Pete wins, he can no longer come in second. So we have 5. Then Snoopy comes in second. And then we have 4 ways, and then 3 ways, and then 2 ways, and 1 ways. When we multiply this out, we get 720 different combinations or ways that those horses can come in that race. So the formula that is in your book, you can really just ignore that because all it boils down to is the total number of ways. Now, how many ways can the horses come in first, second, third, and fourth? Well, here's all I like to do for this is set up now not 6 slots, but only 4 slots. So this represents first place, second place, third place, fourth place. Now, I'm going to erase that because I don't want you to get confused with those multiplication numbers. But here we have 6 ways they can come in first, 5 second, 4 third, and 3 fourth. Then I multiply those together, and that comes out to 360 ways that they can come in first, second, third, or fourth place. So those are 2 examples of a permutation. Now, let's take a look at an example of a combination. Now, like I said, there is a formula for combinations, but I'd rather not go over that. If the PSSAs and Keystones assess you on that, they should give you a formula for it. But here's the kind of problem I could see them giving you. You need to form a team of 3 players, and you have 4 kids to choose from. Without using the combination formula, how many ways can you do this? So I would recommend you just set up 4 kids, and for the sake of saving time, I'm going to call them kid A, B, C, and D. Now, how many ways can I form a team of 3 players? So I'm going to basically just exhaust all of my combinations here. So my first group could be A, B, C. Then I could have A, B, D. Then I could have B, C, D. Then I could have, let's see what else is out there, C, D, A. Then I could have, let's see, C, B, D. No, because B, C, D is already there. A, B, D. A, C, D. Nope, that's right here. And let's see, C, D, A. Yep, we got that right here. B, C, D. So I think those are all of my possible combinations. So I would simply say that there are 4 ways to do that. So the numbers they give you on a standardized test, I think, are going to be doable so that you can just simply exhaust all of your options. I mean, even if there were 5 kids to choose from, if I added a letter E here, it still would not increase my possibilities that much. It would still be very doable to just simply sit there and list them. And once again, the reason why the order does not matter is because I am not giving them any title. If I said the order mattered, then ABC would be different from CBA and BCA and so on. But in this case, it is not. All right, let's take a look at our 2 last parts. I'm sorry. Here we have factorial. So remember that factorials, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And 9 factorial is the same thing. And you can use comma, dot, or not comma, but dot, dot, dot if you'd like. Now, in a problem like this, everything cancels off, and you're going to see that your answer here is 10. Same situation for down here. I'm just going to list them all. 8, 7, 6, 5, 4, 3, 2, 1. And then times the 3 times the 2 times the 1, which is the 3 factorial, divided by 2 times 1. So the only thing that crosses out here is the 2 and the 1. Then I'm going to multiply. And we do this quickly. And then times the 3. So that comes out to 120,960 for my simplifying my factorial. So once again, that exclamation point represents a factorial. All right. Now, let's take a look at the closer here. And this closer, this right here is the formula to use for NPR, it's called. It stands for a permutation. How many ways, or how many people to choose from, chosen this many ways. So here we have 7 people chosen 5 ways, divided by 7 people chosen 3 ways. Well, 7 people chosen 5 ways is the same thing as saying 7 times 6 times 5 times 4 times 3. It's like 5 horses in a race. First place, second place, third, fourth, fifth. 7 choose 3 is first times second times third. Then once again, you will see that we can go ahead and cross out the 7, the 6, the 5, and we are left with 4 times 3, which is 12, which is the answer I told you was to the problem. I wanted you to try to do this to show that the answer does equal 12. So if you would go and do this formula right here, you would have 7 choose 3, which is 7. This would come out to, you'd have to set up 2 different fractions within a fraction, and it would then reduce down to 12 anyways. So keep that in mind. The permutation, the combination formulas are there if you want to use them. I definitely do not think they are necessary. You may learn them later on in your mathematics career, maybe in Algebra 2 and probability statistics later on in the high school. But for now, I think this should get you through. Good luck.